Ah, Houston, my shining city on a swamp. It looks like we have a visitor for today's lecture. But I guess we'll still go ahead and talk about power. And if I had to give my street or perhaps swamp definition of power, it is how fast you are working. It is really just the time rate of change of work. So let's look at a few definitions. The average power is W, not W, over delta T, where this is the work done, and this is the in this interval, right? So if you do a certain amount of work in a certain amount of time, that ratio is just the power. And it's in joules per second, which is equal to a watt. And the abbreviation is big W, right? And it's a lot like average velocity. Remember, average velocity was the displacement over a delta T. We can also think of an instantaneous value at a really small delta T. So if we wanted to look at the instantaneous version, then that would just be P. And just like velocity, we won't put inst at the bottom. If we see no subscript, we mean instantaneous. And that would just be the time rate, the derivative, dw dt. So we can calculate it a couple of different ways. We can also say these are sort of before-after problems, or maybe this would be an initial final state problem. Maybe this is from a graph or something. But if you had a kinematic situation you wanted to apply it to, there's one more useful way to look at it. So let's look at power in kinematics. And by that, I just mean if P is d work d time, well, we could plug in our integral, f dot dr, right, our definition of work. So it's d dt integral of f dot dr. So if you had some varying work and some varying curve, you could figure that all out from this. But there's a simpler version I want to get to, say, for constant force and say for straight line motion, because that would cover a lot of simple kinematics situations. Then what you would have is that the dot product would be sort of a constant. So if the force is always the same direction and the motion is the same direction, they would go together. So we could write this P then as d dt of the force magnitude. Cosine theta is between them, and then you're just left with the integral of dr, the magnitude dr. But then that's just the distance. That's just what you would call d or r, or just how far it went. So then you could say, well, these are constant. They can come out of the d dt, right? So it would be f cosine theta dr dt. But that's just the velocity. This is a very long way of saying if work is f dot d and you take the time derivative and the force is constant, it's the time derivative of the position or of the displacement, which is, as you know, the velocity. So you could say this is f cosine theta v. But you realize, oh, that's the dot product. So now we can make it back, make it general again, and say basically the instantaneous work is the dot product of force and velocity. So now we've gotten away from these approximations actually. At any time, the instantaneous power, I meant to say, is f dot v. So with these three definitions for these different cases, before, after, instantaneous, kinematics, you can work most problems quickly. Because that's power, work them quickly. And now we're going to talk about why sometimes physics is cruel. So in this case, it's actually related to power. Physics is cruel a lot of times. So if I, lift this weight and I sit here and, I'm feeling the burn and everything, and I'm definitely doing work when I lift the weight. Right, I'm applying a force up and I'm getting a displacement up. Right? But when I just hold the weight out like this, which I can barely do, right? What would physics say? I'm not doing any work, right? Because there's no displacement. Oh my God, I'm definitely doing work. And physics says I'm not. That's a case where physics is cruel, right? Physics would say there's no work because there was no displacement. I was just holding it still. In that case, the reality has to do with internal energy, and I am not a solid object like this table. I'm a soft squishy mass, and my body has to do work to make my arm rigid enough to hold up the weight, right? So work is happening inside. I'm doing internal work in here, lots of work, little myosins walking along, but there's no work being done on the weight. So if physics is more specific, it wouldn't seem so cruel. You're not doing any work on the weight when you hold it like that, okay? Let's look at another case where we can actually run some numbers or some equations about work. So another case where physics is cruel is, say you are loading a truck with all your stuff, because the semester's over almost, and you got to take all your stuff home. And you got to load it in the back, and you need to build a ramp. You need a ramp, and you're going to put all your stuff on a cart and roll it up. You got to apply a certain force to overcome the friction and roll it up. And you say, I could get a really short ramp like this. Oh, that would be hard, right? And here's all your stuff, like that, right? All these heavy books that you've been studying all semester, and you push it up here and into the truck. That'd be one option. Or you could say, actually, what would probably be a lot easier is I've got a really long ramp, right, like this. So instead what you could do is you could put all your heavy books that you've been studying all semester on this long ramp and push them all the way up the long ramp. And you would say this was a lot less work, right? A lot easier to do this than this. And of course, what physics is going to say? What is physics is going to say is you did the same amount of work, right? Because the work you did is the potential energy you gained. In both cases, it's the mass of all your books times gravity times how much you raised it, delta y. That's the work you did as you went from here to here. There's delta y, and here to here is the same delta y. And you say, no, that's not right, because this was a lot more work than this, right? But you don't mean work, you mean power. So let's compare the power when we go at a steep angle compared to when we go at a shallow angle. Let's see how much power it takes as a function of angle. So what we're going to say is, in both cases, push the cart at a steady velocity v, right? And we're going to say, well, what is the power? Well, let's see, it's the amount of work you do. It's the change in work, delta W, change in work, over delta T. So it's this mg delta y over delta T, just what physics said we did, mg delta y. All right, but we're going at a constant velocity, so then what do we call delta T? Well, let's see, I guess it takes longer here because we're going farther, right? So if we say the ramp's length is d, right, in both cases it depends on the angle, of course, then d equals vt, then in the bottom you'd put d over v, right? So mg delta y, and this must be d over v, like that. Okay, we could do that. But then let's see, d is going to depend on the angle, so we got to figure that part out. So we got to say, well, it doesn't really matter, we're getting it as a function of theta. Sine theta is opposite over hypotenuse. So sine theta is opposite over hypotenuse d, so d is delta y over sine theta. Right, so this is mg delta y over sine theta. And I guess I could go ahead and put the d up here, or sorry, the v up here as well. All right. Okay, so now we see, this is interesting, so the delta y's cancel, and we get that it is mg v sine theta. Right? So what you find is the work is the same for the two angles of the ramp, but the power is different, right? When the angle is really small, sine of theta is small angle, very low power, right? When the angle is really big, sine of theta gets bigger, go to a higher angle, you got to put out more power to push it at the same speed. So when you say it feels like more work, you really are thinking of power, how much the rate at which your body has having to expend energy sometimes is more important than actually how much energy you expend, more like what you experience. You may look at this and see, actually, we could have calculated this a bunch of ways. You say, wait a minute, this kind of looks like F and V, almost like that dot product, but it's sine instead of cosine. Oh, that just has to do with which way I define the angle, right? If we had to define the angle up here, it would have come out cosine. And then yeah, it is, you could just call this f dot v. So you can calculate a lot of different ways, but you'll always get the same thing, that in this case, the power depends on the angle, so we feel easier when we go at a low angle. So physics is cruel. It is definitely true. All these little cases come up where it tells you you're not really doing what you think you're doing. And we're going to see more of them as we keep going with energy.